Welcome to the second part of our geometry editing in Molflow. So here we have constructed a simple system. The goal was to compare it with this paper, which describes the same system in these schematics. And since this paper is also giving us the resulting pressure profile, and we have seen that it's basically a benchmark system for comparing different pressure simulators, we have constructed the geometry, and now in the second part we will be adding physics and seeing if actually our benchmarking is correct, so if we get the same pressure result. And finally, after that, we'll see some simplification techniques. You can see that this system is symmetrical to the YZ plane, so we will see that actually it's enough to model half of it to gain some speed. Alright, so here we've got the geometry, but so far there is no outgassing and there is no pumping. So let's add the pumps and let's add the outgassing. Going back to this paper, here it writes that we've got two pumps, both of them are 30 liters per second. Now in Molflow, when you go to this simulation button, you can see that right now we're calculating with a gas of mass 28, so let's say nitrogen. And when you click on any facet, you can see that the temperature is room temperature 293 kelvins. So we could actually just select everything and give an outgassing. So for that, we will have to look at the paper again. And here they have been using a thermal desorption rate of 3 to the minus 12 torr times liter per square centimeters. Now, 3 torr equals to 4 millibars. So we could be putting 4 millibars, or since vacuum systems are linear, we could use 3 millibars, because then the pressure profile that we will get in millibars will be comparable with this article, which is expressed in torrs. So I will do that. I will put the numerical value, so I will just put 3 to the minus 12 millibars to my system. So going back to Molflow, you have two ways to define an outgassing. When you click on a facet, like a single facet, you have to choose the directional distribution. Now, most vacuum systems, when you inject gas or when it's coming from the wall, it's obeying the Lambertian or cosine distribution. So most of the cases, you would be using the cosine distribution. And then you could either type an absolute number, like 1 to the minus 3 millibar times liter per second, or since we know the area expressed in square centimeters of this facet, you could put a specific outgassing rate. Now, in case of a single facet, this doesn't mean too much, but when you select multiple, then you can see that there is a difference. So should I put a number here, for example 1, it would mean that every single facet in the system would have an outgassing of 1 millibar times liter per second, regardless of its size. This is not what we want this time. We want to set the same specific outgassing everywhere, and corresponding to the article, we will put 3 to the minus 12 millibar times liter per square centimeter. Now, when you click on a facet, you can see that this corresponds to 4.69. But when I go for a facet with different size, this will be a different value, but the specific outgassing is always the same. So now that we have set up outgassing, we have to add the pumps. So we've got one pump here. This will pump with 30 liters per second. Once again, when I type 30 liters per second, there is an automatic conversion between the sticking factor and the pumping speed. And one thing that is nice to do, that since this is a pump, this is not something that's outgassing. So I will disable the outgassing here. Okay, here we've got another pump. I disabled the outgassing as well. I put the pumping speed of 30. And basically that's it. Our simulation is ready. So before running it, I will just save this file. I will call it ansys with physics. And we can click run. Now, you can see that when you visualize the lines, actually it needs some time until the lines can make it to the pumps. But something is already happening. It's just a little bit difficult to get the pressure from this. If I click on this, and if I click on facet details, I get many details of the facet, like the size, opacity, and so on. What's interesting for me is the pressure, which is like 3 to the minus 9 millibars. If I click on a facet here, I can see a slightly lower value, and so on. The problem is that facets are big and these are average values, so it would be nice to visualize the pressure profile. So one of the easiest way to do that, I will just stop the simulation, is to select everything and add the texture. Later we'll see that there are better ways to do that. So I click on Advanced Facet Profiles, and in theory we want to count the reflection, so like all the particles that are hitting the wall. But also we could count the desorption and absorption. They will be adding to each other. And let's find the texture resolution. Like 1 will result in 212. It's a little bit too many cells. Let's put 0.5 as a resolution. We would have 55,000 texture cells. When I click Apply, the texture is applied to the system. If I click Begin again, then immediately I can see the textures. If you don't see any color, then you have to change the texture scaling. So in Tools and Texture Scaling, I have to click Include Constant Flow, and I could put a linear or a logarithmic scale. So this seems more or less correct. I stop the simulation. So it means that we've got a high pressure, but we've got one pump here, so there is a pressure which is lower there. And we've got another pump there, and obviously as I'm going closer to the pump, the pressure is further decreasing. Now, this is kind of like a solution of the system, but unfortunately, it's still hard to compare with the article because we would be essentially looking for a pressure curve. So Molflow has a visualization tool which is called Profile, and it means that if you get a long rectangular profile, you can visualize the pressure along that curve. Right now, we don't have any such profile. We have to create one. So to do that, it would be nice to get a vertical facet that is running through all the system. So for that, I will go to the front view. And I could switch to vertex selection mode, or even by pressing the Tab key, I can select these two vertices. Actually, I can select everything that's on that line. So you can see that I have selected several. So I will just deselect those that I don't need. So these would be the two first corners of my facet. And the next two corners should be somewhere here, but they don't exist yet. Luckily, there is a command for creating those. So I will just use the project command. And I will project these two vertices to this facet. So for that, the plane is defined by the selected facet, and I will just click on Copy Project Facet. Alright, so now I've got the four corners, and then I can use this vertex create facet from selected and convex R command, and I have selected this profile going all along. If I click UV vectors, then I can see the local coordinate system of this facet. The U is the longer direction, so basically that's what I need. I will just set up a profile running along the U direction. Now, don't forget that this facet is just like a regular facet, so he would be reflecting particles. If I set the opacity to 0, it means that it will become transparent so particles can cross it. And if I put two sides, then he will catch particles from both of his sides. I click Apply. So right now, we still have our textures, but if I go to Tools and Profile Plotter, I can add this curve. And right now, I can see the pressure profile along my system. Actually, if I click on Show Facet, I can put the view in a scaling that it corresponds exactly to the graph. So it would be something like this, and make it a little bit smaller. And yes, here you can see the effect of this pump and the effect of that pump. I will save the simulation. Now, obviously, this is a small system, so I can just put a texture on everything. But if you have created a facet just for counting the textures, then why not remove the existing textures? Let me just disable it. And since it's got a special facet for counting the pressure, I could enable, and I could put even a pretty high resolution because I've got only one. I will just count the transparent passes and run the simulation again. And now you can see that even if I have a tiny resolution chosen, it's absolutely fine memory-wise, so I can get like a more detailed view of this system. Okay, just to be clear, it's pretty easy to select two more vertices, project them to the existing plane. So I could put vertex, project. I could either use the XZ plane, so they will be projected here, but I think it's kind of like cheating, because that way you would be using some specialties of the geometry. So we could very well just choose 1, 2 vertices, and for example 3 vertices, and then you can get the plane automatically from these 3 vertices. Now I go back to the 2 original ones that I wanted to project, and then I say copy project vertex. So now he has created 2 extra vertices, and now using this convex hull command I can actually create my new facet. The last thing to do is to make it two-sided, transparent. I could add, for example, a pressure profile and a texture. And like this, and make sure that I get a profile along the direction. Okay, so right now I will just go back to texture scaling, disable the logarithmic scale, and now you can see the pressure in all the system. Moreover, if you go to profile plotter, now we've got a second profile, which is the vertical curve, basically like a linear curve. I will just remove it now. So, did we actually get the same results as in the article? For that, I will just put Molflow to the left side and the article to the right side. So basically we're starting, this is a logarithmic curve, so I will just put Molflow to logarithmic as well. And you can see that here it's basically 7 to the minus 9. Yeah, it's slightly higher, maybe the system is, actually basically here is, we can see the distance of the system expressed in centimeters, and for Molflow profiles it's always 100 slices. But the pressure profile is exactly the same. We can see that it's crossing 10 to the minus 9 at like basically 30%, which is more or less correct. And then you get an inflection point at the second pump, and finally like a dead volume with a uniform pressure. And since we don't exactly go to the side, like our beginning pressure is slightly higher, I expect that if we would run the simulation longer, then this curve would actually go down. Yeah, as you can see, it's slightly still fluctuating. So alright, so this benchmarking has succeeded. And also like we can see that here it was expressed in millibars, so everything is higher by 33%, and basically you got the same pressure curve between console and Molflow, and it means that so far we have everything in line with the benchmark results. Now, at this point, I will just save the simulation and I will show one final trick. So obviously this is something small, and within a few seconds it has converged. But for larger systems, it's a good idea to take advantage of the symmetry. So what you can do is basically recognize that this system is symmetric to this plane. So we could cut it in half and make a reflecting surface. And that way we could actually just simulate half of the system, resulting in more or less half of twice the speed. So for that thing, what you could do is you could try to select facets on the other side and delete them. But you might have a few facets, for example, this circle, which is spanning across both sides. So it's a good idea to actually make a proper cut. To do that, you have to select the cutting plane. So for that, you will go to the split command. There are several ways to do that. So I could select 3 vertices that are on my cutting plane. Or I could actually select the facet which is in my plane. Or I could even write an equation. So both of them would work. For simplicity, since we know that it's the X and Y plane, I will just click on it, and this is the simplest equation to cut. At this point, I'm selecting all the facets, I'm doing a splitting, and okay, there seems to be, let me check again. Yeah, actually I don't want to cut by the XY plane, which is this one, but the YZ plane, so I made a mistake. Yeah, this is cutting. Let's select everything again and do the splitting, and okay. So my geometry has been split. All those facets that were crossing the plane now has been cut in two. So I will just go to front view. I select everything carefully. Now I can zoom in to make sure that I didn't select some facets in excess, but it seems correct. Yeah, alright, and I will just delete these facets. Okay, and finally I clear isolated vertices. So right now I've got like a system cut in two. I will just save it as symmetric. Now obviously, if I started the simulation, I would get plenty of leaks because everything is going out. So how can I fix this? Basically what I would need is to somehow tell Molflow that the YZ plane is a symmetry plane, and I want particles to reflect when they hit it. It's pretty simple to do that. So a few more things before we actually set up the symmetry plane. So the outgassing, we don't have to adjust anything because basically this is the same. However, for pumps, you can see that he has automatically cut the pumping speed to half. This is because he maintains the sticking factor. So when you're cutting active surfaces, which are pumping or desorbing, make sure that the physical quantities have been scaled accordingly. So far it seems correct. So what I will do is basically I want to create a symmetry plane. And for that I need to think a little bit about coordinates. So basically my system is delimited by these guys. Now if I really just wanted to get my work done quickly, I could just create a symmetry plane like this. After all, it works. Now apparently there is a slight error with this. If I check the coordinates, you can see that the x coordinate, I have selected one which is not exactly on the plane. Yes, this was the culprit. Here I have selected the wrong facet, so I will just delete this facet. I remove this vertex, and once again I will just put this one. Here I have to zoom in somewhat more. And if I did it correctly, then this time I can create a symmetry plane. Yeah, no error message. So okay, this is obviously a very like not elegant solution, but it works. So the normal vector has to be pointing the other way. I will just swap it. And to make a reflective surface, what I do is I go to the advanced menu mode. By default, all the surfaces are reflecting according to the Lambertian rule, but this time I want to make specular reflection, which means that it will be a mirror-like reflection. So if I launch the simulation, you can see that it's still running. Now this time, to get a texture, we could just use simply this symmetry plane. I will just put up a texture. I will count reflections and check if I did everything correctly. So you can see that I get the same results. Obviously, because the texture resolution is not that high, I've got some facets, some texture cells which are half in the system, half not. But still, I can see that the pressure profile is more or less working. Okay, so I have started this solution saying that it's not really elegant, and now I can actually see that there is even an error. Remember that this should be the highest pressure part, and for some reason the pressure is low here. If I turn on the leaks, then I can see why. Basically, here I can see that there is a small part which is not covered by this facet. I could solve it. I show you how to solve it, but still we will make for a more elegant solution. So basically I'm clicking on facet coordinates. If I turn on the vertex index, I can see that this is 78, this is 88, and this is vertex number 33. So basically in between the two, I would need to insert one extra vertex to make it leak tight. I will do that just now. I click here and I say insert before selected row. I apply, and you can see that I have changed it. As for the texture, I will just ask it to be remeshed. I run the simulation again, and now, as we expected, this is the highest pressure part. But still, let's forget this solution because it's pretty ugly and there are better ways to do that. So I will just delete this facet. And now we can actually think a little bit. So we look at the corners of the system, 1, 2, 3, and 4, and I'm asking for the coordinates. So basically, we can see that the Z is between 0 and 500, and the Y is between -100 and 5. So we could use this as one of the coordinates, but we can add some extra vertices. And for that, I will add 500 and -100 here, at 0, and finally at 5. Okay. I'm deleting these, and right now I'm creating a much better facet. Also, I will do the same things. So basically, I will just enable a reflection texture with a relatively big resolution. I will make it specularly reflective. I make sure that the normal vector is pointing the correct way. And okay, now we can see that the system is working nicely aligned with the rest. Okay, and obviously I could make a few reflective surfaces to cover these, but so far this is helping me. And one last thing to do that is I recognize that when you're cutting a few facets into half, I said that it's great to check their outgassing. So some of the surfaces can be actually getting double outgassing because they keep the outgassing, but still the surface is getting to half. So check these basically when you're splitting an active surface, but other than that, this is like a faster simulation. So I will just save this, and thank you for this tutorial. Basically, to summarize, we have created a simple system which exists in literature. We have compared the pressure profile and it was matching with what was published before, and finally we made the simulation faster.